So I'm here to tell you about beam storage and transport, and my talk will echo many of the things that you've heard both during the day and in Jared Maxon's talk. I'm going to start by talking about the rings and the microscopes and the linacs, and then I'm going to spend a few slides talking about emittance. This is that figure of merit that makes for bright beams. And then I will briefly talk about three different scales of beams and their transport. The scale of individual particles, individual electrons. The scale of particle interactions inside a bunch or a packet, and then trains of bunches. Again, as with all of these, the point of this is to give you the vocabulary that you've been hearing all day and you've been a little puzzled by. If there's something I say that sounds like you didn't understand it, this is your chance to ask. Good? So it's quite remarkable, and it's one of the things that this group is doing that's new, is to, as I understand it, coming from the outside, is that we're leveraging the fact that microscopes and accelerators really look the same. They have a lot of the same features. The storage rings and the accelerators, they have these accelerating cavities, and then they have a series of these magnets. Some of them sextuple, some of them quads, some of them dipole magnets, and you tune these magnets to make the beam nice. In an electron microscope, you have a sometimes photo emission source, sometimes other kinds of emission source. You've got an accelerating cavity that brings your electrons in your electron microscope to a high. And then you have all these magnetic lenses, which are the same kinds of magnetic lenses you see here. And I sit in rooms and I hear Georg and David Muller, one an accelerator physicist who thinks about this, and the other one a electron microscopist, and they're trading strategies. Oh, you use chirping to do this. It's really quite fun, and there's some chance that we'll be able to just copy ideas from one group to the other. So the kinds of words you hear, these dipoles, which one is the dipole? The dipole, the blue ones are the dipoles. They bend the electrons around, and then the quadrupoles are these red guys. They come in two different orientations. This was some big deal some generations ago, where they figured out this is called strong focusing, and you can get net focusing by alternating them. And then the sextupoles are the nasty nonlinear guys that screw up your packet shapes and make everything chaotic and make it interesting. The things you're interested in, the emittance that I'll talk a lot about, this is the Hamiltonian system. This is an energy-preserving motion. This is not damped pendulums. This is just the pendulum part. We represent them with area-preserving maps. I'll tell you a little bit about that, but roughly speaking, if you take a particle, watch it cross a point in the ring, wait for it to go all the way around and watch it cross again, that gives you a map where the position and velocity, the position and momentum of the particle as it crosses the first time determines the position and velocity as it crosses the second time. And that will turn out to be a map that preserves phase space area, position and velocity area. There are effects of Coulomb repulsion in all of these systems. There are aberration, all these words you remember from optics, spherical aberration, chromatic aberration, the fact that prisms break up things depending on their wavelength, turns into a problem for lenses and accelerators too, and then chirping and squeezing and many other things that I won't talk about. Emittance. Jared told you about emittance. You've heard about emittance all along. Emittance is basically coming from Liouville's theorem. Some of you have heard about Liouville's theorem in your mechanics course. Some of you heard about it again when you took statistical mechanics. Roughly speaking, Liouville's theorem tells you that if you have an energy-preserving system, a packet with a certain volume and phase space, delta x, delta p, will evolve in time conserving the volume and phase space. Now, when you look at this picture, you're sort of distressed. Okay, it's preserved, but who's going to do an experiment with a volume and phase space that looks like that? This is related in statistical mechanics to entropy. Entropy can be thought of as the probability distribution having a conserved volume and phase space. And that would suggest that entropy would be conserved, because if you have a Hamiltonian describing a dense gas of particles interacting with one another, its volume and phase space is conserved according to the theorems of classical mechanics. But in practice, it gets stretched out into useless stuff, and in practice you see an increase of effective entropy. Your knowledge of what was going on earlier isn't really helpful anymore when it turns into spaghetti. And that's the basis of statistical mechanics, that entropy always increases, which is a statement that emittance always increases. We're a little bit better off here. We can usually keep the emittance sort of under control, but you can lose. So the practical emittance is not this complicated volume and phase space. It's the volume when you surround this by some kind of ellipsoid. And so it's sort of a delta x, delta p, but with y and z. And then the brightness is given by something like the number of particles divided by the degree to which you know where they are in phase space. D is the dimension. So often, so this was the emittance in the x direction, the y direction, the z direction. And it shouldn't be 1 over d. It should be to the d. That was an error. So d, I guess, here is 1 over dimension. That was a joke. What is emittance good for? Well, David Rubin challenged me to add more on emittance, and I came up with this, and I hope I haven't screwed it up. So in the non-relativistic system, like in photocathodes, there's a spot size that your laser hits. So you want to focus the laser as much as possible. And then there's a range in momenta, let's say along the x direction. And the mean transverse energy is twice the energy in the x direction, which is px squared over 2m, which is the expectation value of px squared over 2m. But the px, if the emittance is delta px delta x, that's just the emittance squared in the x direction divided by this quantity. So the mean transverse energy times times delta x times the mass times delta x squared is the emittance squared. Okay, so the mean transverse energy that everyone talks about times the spot size squared tells you what the emittance is. Cool? Now, many of the applications of the idea of emittance happens after you've accelerated it to near the speed of light. So non-relativistic mechanics is not appropriate. So for example, if you want to focus a relativistic beam, the claim is that the spot size delta x times this opening angle is related in a simple way to the emittance. And that's because the z velocity is near the speed of light, you work out the gamma factors and the V's and the thetas, and you come up with this nice formula that the range of thetas times the spot size is given by the emittance in the x direction divided by m times c times this relativistic expansion factor gamma. So again, the better the emittance, the smaller the spot you can focus things down to. You might think, well, I'll just make delta theta bigger. Eventually, delta theta gets too big, but more specifically, you don't want just this spot to be, you'd like a little range, and the delta theta that gets too big makes the range where it's concentrated smaller. Ultrafast electron microscopy, very simple calculation, similar to this, but even simpler, tells you that delta E, delta T is given by the emittance. Okay, so once you have relativistic, if you want a very short pulse and you want it to be monoenergetic, you better have it low emittance. Again, it's the total emittance that's conserved. So if you wanted a short pulse but you didn't mind to have it spread out in the x direction, you could rotate the emittance in a clever way. And that's what lenses and things are for. Now, in rings, emittance is not conserved. Entropy doesn't always increase either. Entropy increases for the world at large, but if you have a damp pendulum, you start off doing all kinds of things, but it always ends up pointing down and in a very low entropy state. In a similar sense, that as you have your particles go round and round in that ring, they emit energy, they get accelerated, they interact with the outside world, they can dump their problems elsewhere, and they end up with an emittance that doesn't really have that much to do with the photoemission source. You still want a bright source because you want a small packet to fit into that dynamic aperture. You remember the dynamic aperture you've been hearing about? This range in phase space where the beam is stable. To aim your beam into that spot, you need a nice bright beam. But once it's there, after a few 100 million turns around the ring, the properties of the beam hardly remember where they started. So the properties in the end depend upon the balance between noise and damping. And I'm going to make an analogy that Raju made earlier, Archishman Raju in his talk, with chemistry. Okay, here's this first return map. Sorry, it's going around this way. And you start with a particle here, and then it'll end up here, and it'll end up here, it'll end up here, and it'll fill in this blue circle completely. However, that demands that as this particle went all the way around, it orbits around this design orbit. It orbits around this design orbit by an irrational number of wiggles this way per circumferential motion. You get that? So the irrational numbers fill out rings, and the rational numbers jump around in like these red things, right? So the rational numbers get all screwed up. And in between these rational numbers, it turns out you have chaos. And so I want you to notice the circular orbits. They're the amazing thing. The fact that there are any circular orbits, not chaos everywhere, took a long time to figure out. And then this red 7 cycle, and then out here you can see chaos. I'll show you another example where the chaos is much more obvious. And that is...
So can I ask a question, Jim?
Yep.
You said,
Yes.
So, well, rational and irrational. How rational and how irrational?
Oh, that's a deep question. So I spent my postdoc working with good irrational numbers and distinguishing them from bad irrational numbers. And I'll come back to that in a moment. I I wanted to make the connection with the three-body problem. This was, why hasn't the Earth left the solar system? You say, well, Newton figured out that it orbited the sun, but there's Jupiter out there. And Jupiter tugs on the Earth too. And if you stick Jupiter in, nobody can solve the equations. And in fact, you do the simple equations, and you say, oh, we're safe for at least 10,000 years. I've done that calculation. We're safe for at least 10,000 years, even with, just Jupiter tugging on us all the time. It'd take that long to throw us out of the solar system. But it's been more than 10,000 years, most of us think. And lots of mathematicians crashed on it. People would come up with these really fancy perturbation theories, and then would try to prove they converged, and they all had what are called small denominators. They had omega 1 minus 5 omega 2 and 3 omega 1, and it turns out that if Jupiter's year is a rational number of Earth years, you can't prove anything. And you can sort of see why here. Here's Jupiter going around. This half is you're going around. You're crossing this thing twice every time you. So this is a 3 cycle. This is a Jupiter year, which is exactly 3 Earth years, which means that Earth is slowed down because we turned Jupiter's mass up so much. And you can see that there's this nice, funny islands, just like those 7 islands you saw before, and in between there's all this chaos. You see that? And that was the discovery of chaos. Poincaré, around the turn of the last century, discovered that the 3-body problem had chaos, and he won all the awards on solving the 3-body problem because he basically said, nah, you can't solve it. The existence of anything that wasn't chaotic, which is really why the Earth hasn't left the solar system, was proven by Coulomb, Arnold, and Moser, and these things are now called KM tori. Why is it a torus? It looks like a sort of a circle, but kind of stretched. Well, the mathematicians don't care about stretching, and you should remember that this is a once-return map that's folded around and goes around this way. Actually, this one goes around this way. This one will go maybe to here, and then to here, and then to here, and then to there. Anyway, it's a tube. Okay, so that's the single particle ignoring the interactions between the electrons, or the ions, or the protons. Are we done? Oh, 4 more minutes. Good. There's the packets that when you put a bunch of electrons in a packet, they have a Coulomb repulsion, right? And Coulomb repulsion makes things push apart. If you're very clever, you can make it push apart and not increase the emittance in some clever way. You can use the fact that all the momenta out there are this way and then push them back in again. I don't know the details, but in practice, it not only pushes them apart, but makes them in funny shape, which should remind you that this is really kind of screwing up your emittance. Coulomb repulsion is therefore bad for microscopes in LINX, where the initial shape of a bunch matters. Why can you go around billions of times without Coulomb repulsion getting worse and worse? Well, partly it's the damping and stuff, but a large part of it is that as you accelerate the electrons, they hardly interact anymore. For example, here are electrons in the lab frame. The electrons' electric fields get Lorentz transformed. If you go back into the bunch frame, this Lorentz contraction gets undone, and they get spread out by this huge amount, and now the density of electrons is much lower. That's one of 2 or 3 factors, I'm told, that in combination dramatically lower the Coulomb interactions. There are other effects about Coulomb interactions. This is sort of the continuum effect. There are also effects when you create them. Sometimes they start really close to one another, and then they sort of push one another and they increase the transverse momentum, and that's called disorder-induced heating. Sometimes if you get even higher densities, they push one another some of them push one another so hard that you lose particles. That's the Touchek effect. There's a whole zoology here. And then finally, bunches will interact with one another. And you've heard people talk about wake fields and things. That if X-rays from one bunch hit the others, these are called wake fields. If the X-rays hit the walls and the walls then bounce off, or if they go through a resonant cavity and they start producing gong as it leaves, you've heard of resonances like bells being hit, then these lead to beam breakup instabilities and resistive wall instabilities, a whole bunch of things. And then finally, you can have these bunches fly through the chamber, hit electrons and ions, sort of residual gases in the chamber, and then get them excited and move around, and then the next time the packet comes down, it messes them up again. So, I give you this as a broad introduction to beam storage and transport.
Questions, comments?
Well, I have my.
In this particle interactions in a bunch, so if I understand it right, that when electrons move very fast in a bunch, because of Lorentz contraction, this Coulomb interaction phases out because this is now a kind of pancake?
Yeah, it's the other way around, actually. I'm suggesting that this is the Lorentz contracted picture, and you say, I've got so many electrons in this tiny volume, and what I'm thinking of is un-Lorentz contracting it into the frame seen by the electrons. The electrons think that they're spread out by a factor of gamma, where gamma is some huge number like.
In the lab frame, the fields pancake.
Yeah. So you can think of it as fields pancaking, and then you have to look up Jackson, or you can go into the lab frame and just spread out your packet by a factor of gamma.
Yeah. Isn't that what you want for them to be as close to each other to be a good bunch?
Yeah, you want them to be close to one another, but you don't want them to repel one another, and you can get both by just going to the speed of light. And I think another factor, I was thinking about this the other day, is the fact that there's also a Lorentz slowing down, that the forces between these particles are causing them to accelerate apart, but because they're moving near the speed of light, they look like their clocks are running slower, and so they don't actually get far apart in the lab frame.
I've also heard that because there's sort of an oscillation around the beam center as they go around, half the time they're being pushed up by their friends, and half the time they're pushed down.
I didn't know that. That's very cool. That's cool. That's cool. Okay. So somehow the Coulomb effects, people start ignoring them when they after that initial acceleration.
It's better than 1 over gamma. The density in the frame goes down by that factor, but then you have to, you can assign a plasma frequency, which then would go down by the square root of that factor, and when you transfer that plasma frequency back to the lab frame, you will see that you get another factor of gamma. And so processes, collective processes, goes down in their time scale, or they expand in time scale by gamma to the 3 halves.
Huh, okay.
Yeah.
So I was wondering what the answer was. I was coming up with various things as I was lying there trying to sleep, and I saw something that said gamma cubed, and who knows?
Gamma cubed is the raw force, but you should, technically, if you're talking about the time scale, you should look for oscillation.
Oh, good. Okay.
Right? So, in fact, the force and then the subsequent motion, that's 1 over gamma cubed. Because the 1 over gamma squared comes from the cancellation of the electric and magnetic fields.
And when I was asleep, I decided that this
1 minus beta
this
squared.
factor was different, though, because the charge in the electron didn't get diluted.
It's a pedagogical way, but it's not going to get you to the right mathematics.
Oh, good, good. Okay, okay.
The electrons may be rocky, right? That's the plasma you were talking about?
Yes. Yeah. Yeah. So the equations of motion always have a 1 over gamma cubed in the
Broad questions. I mean, I don't know, what's happening now?
What's happening now?
Our leadership has to come back before we do the next thing.
So
So other broad questions about the center, about science, about black holes.
Dark matter.
So for the dynamic aperture map that you have, the regions of island stability, you talk about, say, on the Jupiter one, it's a triangle, so it goes one to the next one to the next one. Does that kind of star shape, how does that happen on each of those different islands? Is that always
So-
from
so-
the nearest neighbor or from the furthest neighbor?
It depends on the rotation number. So what he's asking, here I showed you a 7 cycle, and the natural thing to do is to say, oh yeah, it's going around. But maybe this one was doing this. You remember, it's a question of whether omega 1 around this way and omega 2 around this way are rationally related.
There's both a numerator and a denominator.
And so this is likely to be doing this, right? It can be going forward twice each time, or it can be going forward 3 each time, like that. That's technicality, but it's kind of fun to think about these tori. So this is another KAM torus. It's just a very funny knot of a KAM torus, but it's surviving its integrity, its mathematical robustness to small perturbations, as long as you have good irrational winding numbers.
So then, can you explain that?
So
It's a good irrational.
a good irrational is one that cannot be approximated well by rationals.
But any irrational number has
So-
a rational one.
So if you take the continued fraction expansion,
Okay.
then if you've ever heard of a continued fraction, I had an unfair advantage as a postdoc because I had studied a little bit of number theory. If you take the continued fraction expansion, if there's a big number in the integers in the continued fraction expansion, 1 over 1 plus a over 1 plus b over 1 plus c over 1 plus d, where a, b, c, and d are integers, can approximate any irrational number. A rational number is one where there's an infinity somewhere along there, so you can basically truncate at the previous level. And an irrational number that has some very big numbers in it. One big number isn't bad enough, but if you have big numbers over and over again, so 1 over 1 plus 1 over 10 plus 1 over 10 to the 10 plus 1 over 10 to the 10 to the 10, that will be a Liouville number, which will you can't prove it won't go chaotic. But if you avoid the Liouville numbers, there's a set of measure 1 of irrational numbers, which are good irrationals, whose tori will be preserved.
What about cubic root from 13? Is this good irrational number?
Pardon?
What about cubic root from 13?
Cube root of 13? Cube root of 13 is a good irrational. All quadratic, all algebraic numbers that are not rational, I believe, are good irrationals. All things, the most irrational number? No. Pi is not particularly irrational. It's a golden mean. It's 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 is the golden mean. Square root of 5 plus 1 over 2. Square root of 5 is not quite as good. Square root of 5 plus 1 over 2 is good.
So this number theory gave you this brain damage.
Well, it's even more. If you have something that looks like with square roots, then you have a periodic continued fraction. You can do the renormalization group. Yes.
So you say you have chaos, for instance, in between those little.
You can't see it here, but you can see it nicely. You can see it here.
Are there, when you say there's chaos, do you still like stay within that region?
Yep. Well, excellent question. If you have a two-dimensional map, then the KM tori surround the chaos and they can't get out. But if you're in higher dimensions, in principle, each of these chaotic regions, because in a real map, there's not px and x, but py and y. In a real map, it's thought that all these chaotic regions will eventually leak out via something called Arnold diffusion. And one of the things that Archishman and I are doing is ignoring that. And that gives us an immense advantage over all the people who really want to prove theorems. It looks like we have some higher authorities coming back. Are we ready to go on to the next stage?
We are supposed to split in 3 teams.
Yes.